I think we're getting set up, and looking forward to your talk.
Awesome. Thank you, Martin, for the introduction. So yeah, like he said, I'm super excited to be here in particular because I haven't been back since I finished my PhD here at Penn. Also because it's the first time I'm attending CoLLAs. So I'm very excited to tell you a little bit about my thoughts on how we can leverage modularity to enable a stronger form of lifelong learning in robots that will hopefully eventually enable us to deploy robots in people's homes. So if we want to have a home assistant robot in every household, it's pretty clear that these robots will need to be versatile and adaptive. We'll expect them to have all sorts of capabilities. And each of us will also expect our own robot to adapt to the chores we need from it, how we like them done, the tools and appliances in our home. And what's more, our needs, preferences, and environment are all likely to change over time. And so 5 years ago, we were all trying to convince the community that it was a bad idea to train a separate model to solve each of these problems, because then the robot would not reuse any of its knowledge about previous chores to allow it to do later chores. And so largely we have kind of succeeded at that. And now the community has converged on this idea that we can train these very large models in batch over a collection of problems. And that has been super successful both outside robotics and in robotics. But the one big assumption that this makes is that it'll be somehow possible to cover the entirety of the future experiences that the robot might ever have, including the layout of your home, your specific preferences. And I argue that this is by far the greatest, or greater than any generalization challenge than we have ever been able to actually solve. And so with that, it continues to be incredibly necessary to do lifelong learning in order to actually have versatile robots. And the main insight that I'll share today, so if you'll take away just one thing from my talk today, is that modularity is the key that will make this problem feasible. Because robot problems are amenable to modular solutions, and modular solutions give us a range of advantages for lifelong learning. So let's set up the stage and start by taking this view on forgetting. So suppose you have your robot, it's tackling the current task. And in some sense, it might be the best thing to do to solve the current task could be to just very aggressively adapt all of the agent's models and essentially overfit to the current task. But then the robot would never accumulate any knowledge about the past that might be useful for the future. So for example, if our robot is right now learning to open our Amazon packages, knowledge about food and doors is not really relevant. But it might be in the future if we ask the robot to put the groceries in the cabinets. And so with this view, avoiding forgetting is really about enabling generalization to the future. So let's talk a little bit about how modularity can help us do lifelong learning in this context. The standard solution that people think about when we talk about continual learning is we're going to take one monolithic neural net, we're going to train it to solve all the problems that we'll ever face. So for example, if we train our robot to put the leftovers in the fridge, it might end up encoding knowledge in this network about how to open the door of the fridge, how to grasp these small wrappers and leftover boxes and bottles, all mixed in this giant network of weights. And if we then want a robot to solve a new problem, like opening our packages, even if the robot knows that it should retain that knowledge about opening doors for whatever future problem, because knowledge is all tangled up in this network of weights, the robot is largely doomed to overwrite some of that useful knowledge. So modularity gives us 3 key benefits in this lifelong setting. First, the robot can encode each piece of knowledge in one self-contained unit and then target updates to modules individually. Second, the robot can progressively add more modules over time to handle broader sets of problems. And third, the robot can combine modules in new ways to solve tasks compositionally. And then you may wonder, okay, so what are these modules? What are useful modules that can help us solve robot problems? And today I'm going to focus on two forms of modularity on compositionality. So at the temporal level, the robot might decompose its decision-making process into high-level or abstract actions like navigate to an object, pick up an object, place the object. Well, at the functional level, we can decompose problems into processing stages or subroutines, like perceive the state, make a plan to achieve the goal, control the motors to follow that plan. So for example, if our policies take as input, say, an image of the world and output motor commands, the temporal modularity is analogous to running different policies or options at various stages of solving a task, while the functional modularity is akin to a single policy composed of multiple processing stages. So for example, suppose we want this orange EWA robot to place the box in the bin to its right. It can leverage temporal modules for picking the box, lifting it off the table, and placing it from the top. And if we then want to solve a similar task, like placing on this shelf, we can leverage the picking and the lifting modules and use a new module for placing from the side. But what happens if instead we want to solve the same original task, but with a new robot arm, like this black Jaco arm? The temporal modules wouldn't actually help us because they are specialized to the orange arm. But if we used a functional decomposition, we could swap out a module that drives the EWA motors by one that drives the Jaco motors and leverage the post-detection and trajectory planning, which are exactly the same for both robots. So in the first half of the talk today, I am going to cover a solution that leverages the functional type of modularity. And our goal is going to be to learn a modular neural net to solve a large collection of robot problems. So in this setting, the robot will solve each of these modular subtasks in some abstract embedding space that constitutes the interface for communicating between modules. So for example, if we want to solve tasks such as placing the box on the shelf, throwing the box in the bin, placing the plate on the shelf and throwing it in the bin, both with the orange arm and the black arm, we can do this by doing something like we train a small neural net to determine the gripper post to interact with the box and one for the plate, one for planning a trajectory for throwing in the bin, and one for placing on the shelf, and one for controlling the motors of the orange arm, and one for the black arm. And then we can stack all the networks in a path to form a solution. So the first module gives us a post for the gripper for the trajectory planner. The trajectory planner gives us a path of the gripper for the joint space controller, and the motor controller gives us the actual motor commands. So we're building a separate neural net for each task by building or by composing all the pieces that we have. So, to make it a little bit more concrete, we, for example, have pass our state as input through a set of modules that we choose to construct one policy. We get an action at the output, and then we pass the next state as input through the same set of modules to compute the next action, and we do this again and again until we complete a whole trajectory, for example. And so more generally, we can think of a problem graph to represent these kinds of robot problems. And the key is to think about this in terms of two assumptions. The first one is that solving a robot problem can be done by sequencing a chain of transformations that progressively transform an input observation into an output action. And then the second assumption is that we can reuse these transformations by combining them in multiple different ways to solve various tasks. And with this, the compositional problem graph is a directed graph with two types of nodes. The first type are the observations and actions of each task. And the second type, which is the interesting type, are the functional transformations, such that if there's an edge from F1 to F2, then F2 takes as input the output of F1. And the solution to a task is a path through the graph from input to output. And then we can use a small neural net to represent each of these functional nodes and stack all the nets in a path to form a solution. And so, okay, first question we asked ourselves was, can we actually use this kind of structure to solve a bunch of robotics tasks? And so we created a large benchmark of manipulation problems, and we trained the whole graph of neural net modules end-to-end using PPO. So we never say, what is the output of each module, but we do build the graph. We train it end-to-end with PPO, and we were able to solve the 256 different manipulation tasks by just piecing these things together. And so we have some nice numerical results. Happy to talk about them offline. But the key thing that I took away from these results is that in order to obtain the kind of the nice benefits that we want from modularity, like forward transfer and compositional zero-shot generalization to new problems, we actually had to train on a very, very large collection of tasks. And this is a big problem because in the lifelong setting, the robot only ever sees one task at a time. So how can we enable this kind of generalization that requires many training tasks? And so I'm going to talk to you about the solution that we came up with in our work, which relied on the idea that we can split the training process for each new task into two stages, where the first stage is just focused on solving the current task. So we leverage whatever we have learned so far, we compose the modules that we have learned, and then we depart from them with the help of some additional modules to avoid enforcing exact compositionality of things that are still in the process of being learned. And then we're going to take any new knowledge that we acquired in these helper modules, and we're going to push it into our compositional system so we can use it in the future. So first stage in adaptation, we only worry about the current task. And then in the second consolidation stage, we worry about how that might fit with the rest of the knowledge for the future. So to make it a little bit more concrete, what we're going to do is we're going to train in the adaptation stage a separate neural net for the new task, initialized with the parameters of the modules that we have acquired so far. So we got the first task. We don't have any modules yet, so we just do PPO training. We obtain a policy. Then we use our consolidation stage to push these modules into our kind of repository. I'm going to talk about consolidation in just a moment. Then we get the second task. And if this task requires any module that we have already seen, we are going to initialize that module's parameters with the parameters of the corresponding module that we have already trained. And then on top of that, we do our standard PPO training and follow consolidation to store whatever new modules we got. And so the key intuition here is that we're trying to build a policy to solve the new task by putting pieces together from all the previous tasks that we have trained. And so we keep doing this for every new task. And early on, we're going to face tasks that probably require some completely new modules, things we have never seen before. And so even if we use this kind of compositionality, we're still going to start out with a completely random policy. But over time, the agent is likely to face tasks that are just new combinations of things it already knows. And so we can start with a full compositional policy. But because we don't trust that these things are yet trained well enough, because in a lifelong setting, early on, we don't have a lot of data, we're still going to do PPO training to make sure that we can solve this current task that we care about. And then in the consolidation stage, our goal is going to be to end up with a collection of modules, one module of each of these colors, that has been trained on so many tasks that it eventually generalizes to any new task that it faces. And of course, this is now our typical continual learning challenge where we want to we are not allowed to actually go back and interact with the environment for all those earlier tasks, but we still want to maintain the knowledge that we acquired throughout those tasks, because that is what will allow us to generalize to any future task. And so, you know, we think about this as a simple replay problem. But in this reinforcement learning context, we actually have to be a little bit careful about how we do our replay, because if we just say, okay, let's just maximize performance over the set of tasks, we quickly end up in a situation where the distribution of states that our policy visits is very different from the distribution of states that we have seen in our training, and our performance drastically degrades. And so, the big insight that we came up with, and I think this is already a thing that a lot of people are doing, but back then it was pretty new, is that we can treat this, or we can cast this as a multitask offline RL problem. And so what we can do is we treat the data sets that we have acquired in the past as fixed data sets and apply off-the-shelf offline RL methods on that data, which is basically going to prevent that kind of distribution mismatch. And the key difference here is that when we apply this to our modular solutions, what we can do is we only need to consider tasks that share some of the modules that our current task uses, and we only need to update the modules that our current task uses, right? So we don't need to touch anything else. So again, we got some nice numerical results. This time we did this in mini-grid. And the nice thing about these results is that what we see is that as the agent is trained on more and more tasks, it is able to more effectively generalize zero-shot to the next task. And then, of course, we continue our training, right? So this is just like one snapshot at the beginning of each task's training, where the agent is already able to piece its knowledge together to achieve relatively high performance. And this improves over time. Okay, just some takeaways and caveats about this first part of the talk. So the first one, big one, is modularity actually helps us do lifelong robot learning substantially better than monolithic solutions. The second big one is that modularity makes it easy to at least reduce the amount of forgetting, because we can say something like, okay, I am right now just focusing on opening doors. I don't need to worry about my policy to sweep the floor. I don't need to worry about any other thing. All I need to do is update whatever it is that I am doing right now. And third, and this is maybe a slightly more nuanced point, one very useful thing to do when continually training models is to do as much learning as we possibly can without touching any shared parameters. And so we essentially, if we find ways to figure out how to solve our problem before we ever touch any of the shared parameters, that allows us to leverage that knowledge about the task to do our training of shared parameters significantly more efficiently and reduce forgetting, which again helps us with generalization. Okay, one big caveat for all these results, I actually manually told the system how to compose modules together. So I knew what was the structure to solve each task. I didn't say this module should output this thing, but I did say, here's how they should be pieced together. And so we do have techniques for how to sort of automatically discover useful ways to compose modules. And I guess here comes the kind of the final point that I want to highlight here, is that the key to achieving that is to design modular solutions that don't rely on finding an exact, perfect, single modular composition that is the only one that works. Essentially, we need some flexibility such that if whatever compositional solution we find is not exactly the right one, the system is still able to perform well. Basically, we go from trying to find a needle in a haystack to trying to find just one of many possible solutions that could work. And then if we go back to our robotics setting, one challenge with the solution that I've been talking about so far is that current reinforcement learning and even behavior cloning methods are really great for finding high quality control policies for very short horizon problems, like the picking and placing tasks in our Compass Suite benchmark, but they struggle when faced with longer horizon problems like the household chores we started out. And the key to enabling these longer horizon behaviors is to go beyond the functional modularity of our modular nets and incorporate also temporal modularity. And this is what I'm going to talk about in the second part of the talk. And so task and motion planning is one kind of robot planning mechanism that embodies both temporal and functional modularity. So because I assume people in the audience are not too familiar with task and motion planning, I'm going to give you kind of a brief primer. So the basic idea is we're going to split the robot's decision-making process into two planning stages. The first stage is at the task level, for which we just use classical AI planning. So think operators and preconditions and effects. And the outcome of this task planning stage is an abstract plan, a sequence of high-level actions, such as like navigate to the fridge, open the door of the fridge, navigate to the oatmeal, pick the oatmeal, and so on. Now, making decisions in this very modular way is exactly what enables us to solve truly long horizon problems. And then for each of these abstract actions in our plan, we're going, at the motion planning level, we're going to use some form of parameterized controller. So, for example, if we want to execute the action to move from the counter to the fridge, we're going to use some sort of navigation controller that takes as input the target XY coordinates and produce a collision-free path. And here the key challenge is coming up with those XY coordinates, the continuous parameters for how we should execute the abstract action. And so in task and motion planning, or at least one way to do task and motion planning, is to sample continuous parameters from some distribution and try a bunch of those in a simulator until we find a sequence of these continuous parameters that allows us to execute the entire abstract plan. And so just to kind of give you a sense for how this goes, suppose that our goal here is for this fetch robot to push that box into the screen, and it has to execute 3 actions. Navigate to the box, attach itself to the box, and push. And so if we focus on the navigation action and we say the continuous parameters are going to be the delta x, delta y with respect to the center of the box, and this sampling-based planner is going to attempt a bunch of XY pairs until it finds a coordinate pair that both comes within reach of the box and avoids collision with anything in the environment. But the big challenge is that the robot might realize later in the sequence that the chosen parameters didn't actually enable it to solve the task. Right? And so it has to essentially backtrack until it finds a parameter pair that actually enables pushing the box into the screen. And so our goal in this problem was to learn a distribution of the continuous parameters that, for example, in this case, allowed the robot to eventually push the box into the screen. And so the problem setting that we considered was, suppose we have a task and motion planning system. It already works, but it uses very low quality parameter samplers, say a uniform distribution over the entire space. So what we're going to do is we're going to use that sort of low quality task motion planning system, and we're going to try to solve our first problem with that. And it might take forever because now we have to try all possible parameters until eventually we land upon a sequence that works. But what we're going to do is we're going to take whatever parameters actually worked. We're going to build a small data set, and we're going to use that to train our sampler to get a little bit better. And we're going to try to solve the second problem. Hopefully, we're going to be a little bit better than we were before. And we're going to do the same. We're going to keep the parameters that actually worked, construct a small data set, and train our samplers a little bit. And then we're going to repeat this process again and again and again. And the key thing that allows us to do this is that this rejection sampling procedure allows us to construct a data set of good samples from a poor sampler. And then I guess one thing that I wanted to highlight about this problem is that it gives rise to what I found to be a particularly interesting form of a sort of multitask problem, where suppose we're trying to learn the samplers to pick up objects, and we have all sorts of different types of objects like pens and boxes and coffee mugs. And I think we've all at some point thought about a problem like this where we're like, well, should we train like a separate neural net to do in this case, the sampling for each type of object? Or should we just train kind of a general purpose neural net that knows how to grasp all types of objects? And the big challenge to answer this question is that, it depends on a bunch of factors, like how similar are the objects? How much data do I have for each type of object? And then the answer to these questions in a lifelong setting actually changes over time. And the big piece of insight that we got here was, well, we're in a task and motion planning setting. We actually don't need every single sample that we generate to be good. Our goal really is to mostly generate good samples and to cover the majority of the space of possibly good samples. And then what we can do is, well, we sometimes draw samples from the generic distribution. sometimes draw samples from the specialized distribution, and then we just let the TAM system figure out which of those samples are good. And the intuition, again, is that it's really hard to tell ahead of time what is the right choice. Which of these two types of models should we train? So we're just going to train them both. So we're going to train a generic distribution. In this case, we used a diffusion model to represent that. We're going to train a specialized distribution for each type of object. And then the actual distribution that we will draw samples from is going to be a mixture of the two distributions, which is going to allow us to have broader coverage over the entire space of possible parameters. When you get to the technical level, the only kind of piece of thing missing is how do we determine these mixture weights? And I'm not going to get into it in the interest of time, but super briefly, the key idea is that we can use auxiliary tasks to essentially measure how much does the current state fit in distribution for both the generic model and the specialized model, and then use that to tune the knob of how we weight these two models. Right, so just as a brief teaser for the results, we put this in a simulated kind of household environment. We asked our fetch robot to put everything inside the fridge. It tries this a bunch of times over a collection of different initial states and so on. And it learns these distributions, the red dots that you see floating around, for how to interact with each of the objects. Then it moves to a new setting and it translates that to, now picking up cans, which are somewhat similar, but not exactly the same. So then it specializes to those over time. And then it continues to do this after a collection of large tasks. I think we did something like over 1,000 or 2,000 tasks in sequence. So, okay, takeaways from this second part of the talk. First big one is that by leveraging both functional modularity and temporal modularity, we're actually able to solve some pretty challenging robotics problems, like those fetch examples that I was showing you. Second one is I think we came up with what is a fairly interesting and unique problem formulation for lifelong learning, which is if you have a generative model setting where you have access to a verification mechanism that can tell you whether your samples are good or not, you can start out with a very small data set, use that to train a pretty bad but slightly better than random generative model, generate more data, use your verifier to figure out which of the samples are good, and then kind of bootstrap this way. And so it's a problem setting that I think could be interesting in various domains. And then within this setting, there you go. And then within this setting, we don't actually have to make a choice of what is the exact model that we should train. Should we train like a single task model, a multi-task model, a small model, a big model, a model that uses images or states or whatever it is? We actually can train a bunch of different models and build mixture distributions out of all of them, which is actually going to help us have broader coverage of the distributions, which our verifier can again then just discard the things that didn't work. So I think this is actually pretty interesting. Okay, so just to wrap up, I'll briefly talk about what my vision is for how we can continue to develop these ideas into lifelong learning algorithms that will let us put robots in people's homes. So what I envision is that we'll construct a system that has a bunch of robot capabilities, and we'll do this prior to deployment with some combination of large-scale pre-training and engineering. And the key thing that I think is relevant here is that we should find ways to construct pre-trained models that are by design constructed to be adaptive in the future, rather than just taking whatever pre-trained models we have and focusing on how we might be able to adapt those. Then we'll put our robots in homes, and each robot will have a range of experiences. It'll leverage its data from its home, and it'll use that to become more efficient and more effective at solving tasks in its particular environment for its particular user. And I would say that in this context of single robot learning, it's, I guess, where we have made the most progress, but there's still a bunch of things that we need to do. And I would say that one of the biggest things that has been holding us back, at least in robotics, is that the problem formulation of training over a sequence of machine learning tasks and then evaluating over the sequence of machine learning tasks that we trained on is not really compatible with what we want, right? We need to come up with problem formulations that better capture the notion that what we want is a robot that is potentially training a large collection of models to do all sorts of different things, including perception and acting and planning. And then what we really care about is that the robot is right now able to do the thing that I asked it to do. And then finally, if we're deploying many of these robots in many people's homes, then we would like to be able to leverage this kind of large scale data that we will get, but we need to be mindful to do it in a way that both maintains specialization to each individual user and also respects the privacy of each user while sharing this kind of knowledge across users. And I believe that modularity is going to be the key thing that is going to allow us to solve each of these problems in various ways. And I'm happy to talk a little bit more about that offline, but I'm probably out of time. So I will thank all the collaborators, especially those here at Penn that helped me throughout all these projects. And with that, I'll open it up for questions if we have time.
Yeah, thank you for the nice talk. We're out of time, but I think we can do questions because it's just a coffee break.
Yeah, so nice talk. But for the purposes of my question, I'll play the role of a reviewer too.
Yeah.
So early in your talk, you argued for sort of using explicit modularity, meaning you kind of include a lot of engineering components that select tasks and sort of consolidate them and so on. But it's been observed that large deep neural networks, particularly with value activation functions, tend to have sparse activation, which you can interpret as sort of sub-networks, and huge networks with sparse activations tend to not have this catastrophic interference because they tend to activate sparse components. So can you contrast like using explicit modularity versus sort of implicit modularity and the case for both?
Yeah, great. I love that question. I mean, I think so we would all love to have an algorithm that can sort of discover all of this on its own, right? So through some form of implicit modularity, maybe we impose some sparse heated regularization. And if somebody's able to come up with that in a way that allows us both to reuse the things that we have learned in the past to very quickly learn in the future, and also be able to kind of protect the pieces of knowledge that we want to protect because they're isolated units that came up spontaneously during training, then I would be all for that. I have yet to see a system that achieves that, but I am by no means claiming that it is infeasible. I think my claim is more that however our modularity comes about, whether it's because we designed it, and I think in robotics it makes a lot of sense to design it, but there may be a lot of other fields where that's not true, right? So, people try to do this in language for a long time and in vision for a long time, and the empirical evidence ended up saying, well, I guess we don't have such good knowledge about these, or prior knowledge about these, to construct solutions that are as good as whatever we could just train. So if we're able to just automatically learn that, then by all means, I think that would be great.
Okay, I have a quick question. Is I don't disagree with the modularity, but would this modules becomes infinite number of those modules? Because if I grab things this way, I grab things this way, I grab this way, I grab this. You all need kind of every angle I grab, I need new policy to be trained. I think the humans seem to have a self-awareness. I know what I can do, and although I never grab something from here, but I'm pretty sure I can do it.
Yes, great. So I'm going to tackle that question from kind of. So the first thing I'll say, I guess that comes from the example where I say, well, we need one module to place from the top and one module to place from the side. In practice, in that setting, I actually think that is what we did, but I don't necessarily think our modules should be that way. Right. So in some sense, finding the sweet spot between how general should our modules be versus how hard would it then be to maintain those modules and grow them over time. That is a really hard question. I don't know the answer to it. But at some intuitive level, the good thing about modularity is that it allows us to essentially leverage combinatorial explosion. right? So we can, once we have a relatively small collection of modules, we can compose them in all sorts of different ways to solve many, many problems. And I think we are on the way to figuring out how to leverage that to our advantage. And as one small example, the Compost Suite benchmark, it has 256 tasks, but we only need 16 very small modules, and we can piece them together in 256 different ways to solve all those tasks. So I think there's caveats, and I'm not saying that these are the solutions, but I do continue to believe that modularity is going to be helpful. Thank you.
Oh, hello. I actually had a very similar question, so I just want to do a follow-up. Like you mentioned that the way you break up the tasks doesn't matter. Or actually, in the previous question, you actually think about certain criteria for finding a good decomposition of the tasks, such as having a very compact set of tasks so that we can train lesser modules as possible. And also, I think another idea to find a good so-called optimal optimization could be finding tasks that are shared, or like actions that are shared in a lot of previous actions in previous, say, if you already have a large benchmark of robotic tasks, then it can be optimized to learn such subcomponents through optimization.
Great. Okay. Yeah. Thank you. So I guess two thoughts. First off, I don't think I actually, or at least what I meant to convey is not that it doesn't matter how we split our tasks into components. It actually matters a lot. And I think the key comment that I was making is that if our algorithms rely on finding a single perfect optimal solution and otherwise they don't work, then we're doomed to fail, right? Because we're doing this from statistics, we're doing this based on data sets that are incomplete and that don't cover the entire space of solutions. And so my claim is that while we should strive to learn, as sparse and small a collection of modules as possible, we need to sort of deal with the fact that the modular solutions that we can automatically find are not going to be perfect. And we need systems that are able to account for that somehow. And then your second point, which was about leveraging essentially reusability as a driver for choosing modules, I 100% agree. I think I don't know how to do that, but if we can do that, that would be fantastic. Yes, I agree.
Thanks
Thank
a
you.
lot.
Very short, please.
All right, George, thank you very much. Really love your vision and refreshing talks, and I share a lot your ideas. And in relation to the problem points there about the manual modular structures, right? We struggle as well when you have like dozens of modules, and we had some success trying to match the modules and policies with a task using some measure of task similarity. I wonder if you have thought about it and maybe considering it.
I see. So essentially trying to compress modules together once you figure out like you have modules that are too similar. Is that kind of where you're going?
No, you try to assess the task, the new
okay.
task in relation to all the tasks that you have learned. And then you try to get the best guess for what are the closest types of policies
I
that
see.
would help me.
Yeah.
And of course, then you would have to fine tune a little bit, maybe close the gap.
Okay, yeah. So I guess in some sense, when I said we have some techniques to actually do this automatically, they kind of go in that direction. So we did a pretty naive discrete search over our modules and basically pieced them together in all sorts of ways to find out which is the combination that most looks like it could work for this task, and then go from there. One of the other things that we've been doing a lot is more leveraging kind of the structure of robotics. So things like, well, when contact points change, we know that maybe that corresponds to a skill change and things like that. But I think there's also all sorts of ideas that can come together from both the kind of the how similar does this look to what I've done before versus, oh, I know these things about geometry and physics that I can also leverage to drive my modular design. Yeah, happy to talk more about that.